Hello, people of the internet. Welcome to Physical Sound Synthesis. This is a video I've been wanting to make for a while, and I'm going to talk for a bit in this introduction, so I drew some very excited guy saying, yeah, he's excited for this, because this is a long time in the making. I've tried making this video a couple times, but never went through with it, but that's okay. So let's get started. What is physical sound synthesis? It's this idea of I want to make sounds with my computer using math. But what does that mean? It means we have instruments like a guitar or a piano or what have you, and they make cool sounds. And we want to understand how those sounds are created and how we can mimic them. And maybe if we can mimic them kind of nicely, then we can design our own sounds, which is kind of a cool idea. I mean, maybe in theory, if you get really good at this, you don't need to experiment with, I don't know, what kind of wood you're using in your piano or the type of guitar strings. You just model it all with math and figure out what works nicely, and then boom, you have an instrument. It's not really quite that simple, but it's a nice idea. So what I wanted to do today is just introduce these concepts, like the foundational concepts for this, and then maybe in some other videos I'll actually write some code and make some sounds. So this one's just going to be about some theory. So I guess a nice place to start is a string instrument. We can actually write down with our math and physics some nice models that work pretty nicely of a string instrument. So it kind of helps think about, okay, what is a string instrument? That's the starting point. Time to draw. I got my Wacom pen tablet here, so expert drawings inbound. So if we imagine our guitar and just a string on it, one of the strings, or even a piano, any sort of string instrument, we have these two fixed points, and then between them is a string. And when we pull the string back, whether with our pick or we hit it with a hammer on a piano or some violin bow, basically gets stretched out. And then we let it go, and then it's going to kind of come down, and then it's going to go back up, and down and up, down and up, down and up in this oscillating fashion, and we hear some amazing sound come out. And if we were to capture the sound with a microphone and plot the frequencies of the sound coming out, we'd see something kind of interesting. It's not just one frequency or one pitch that we see. We can draw a little plot of, on this x-axis, frequency with F, and the y-axis, how strong it is. We can call that the strength of the frequency F. We would see at some point, we can call it F0, that what we call a fundamental frequency, the first pitch. We get some peak. We can do this in another color. And then we'd see at twice F0 another peak of some other strength. It could be even taller than it. And then at the third, I'm trying to draw these equally spaced, so that one there is 3 times F0. We'd see another peak. It could be smaller, let's say. And you can see the pattern, on and on. We get all these harmonics, they're called, and they're more or less equally spaced by this by the fundamental frequency. So the spacing between any two of these is typically just about F0. So we could say that the pitch of any of these frequencies is called the nth pitch. So Fn is just about n times F0. So F1 is 1 times F, or really it would be n plus 1, but you know what I'm saying. Fn, we could say Fn equals n plus 1 times F0. And that way when n is 0, we get F0. When n is 1, for the next, for this one, we'd get 2 times F0, 3 times F0, etc., on and on. So that's the basic idea. So we want to develop some sort of mathematical physical model that produces this result, because we know with our ears or with our computer that captures a sound and plots this frequency against strength of frequency, we know we get this result. So we need some sort of mathematical model that captures this. Well, one model that captures this is something called the wave equation. And I'll just write it down for now. it says that this is the second derivative with respect to x of our string, the displacement of our string, let's call it y, is equal to 1 over the velocity squared of our string, or of our string, times the second time derivative of the displacement of our string. That's a bunch of math nonsense. It's not nonsense, but if you've never seen this, it won't make any sense, but that's okay. But the result of this, which we're actually going to come back, we're going to circle back to this. So this is a little confusing, this stuff here. That's okay. We're actually going to come to this equation with more basic calculus and basic physics. But the result of this equation is exactly the result here, that we get all these oscillators that are oscillating at these frequencies, the fundamental, 2 times the fundamental, 3 times the fundamental. We get that result. So writing that down a little mathematically, that how the sound or the displacement of the string corresponds to the sound. So the movement of the string or the sound of the string as a function of time is really some coefficient, we can call it a naught, times, let's say, a sine wave at frequency f naught, so 2 pi f naught times t, plus a1, so some other coefficient, sine 2 pi f1 times t, on, until however many harmonics we get. And if you haven't seen a sine wave in a while, that's okay. I'll write that down real quick. Basically, if you write down time on the x-axis, the horizontal, and the amplitude, the y of t, on the vertical axis, and if we just looked at, let's say, one of these sine waves, a naught, we would see that it looks something like this. A little curve, up and down, up and down. And these, the distance between these periodic structures is the frequency, and the height of it, say that's the height from 0 up to the height, is this amplitude a0. And then if we can draw below it, let's say, and this is going to be, that top one was a naught sine 2 pi f naught times t. And below it, we're going to draw, if y of t was a1 sine 2 pi, and we're going to have f1, which is really 2 times f naught, so I'll just write that there. 2 times f naught times t. So recall that the spacing between these little structures is f naught. It's really 1 over f naught, but that's okay. The frequency of that. Basically how quickly it's moving up and down. So if we have twice that, or right here, 2 times f naught, we'd expect the structure to happen twice as quickly. So if we draw a little dotted line so we can line this up nicely, we should get twice as many of these structures between any 2 full cycles of the previous structure. So we can keep doing this. And you can see that the spacing of this sine wave, these little things are called sine waves, these blue curves, of this bottom one is 2 times this one. This one is half as fast. And so our ears perceive that as twice the pitch, a different pitch. And we're going back to this model here we've written down. And if you haven't seen this math before, that's okay. I'm going to go through it. This model, when we solve for y, kind of like an algebraic equation, you have some x's and some constants, and you want to solve for the x's. In this case, we're solving for y. When we solve for it, we get these sine waves at different frequencies that are integer related to each other. So what I want to do now is actually see where this model comes from. And it's actually not too crazy, so don't worry. So if we take our string again, if we were to zoom in, sorry, let's draw that a little better. These are the fixed points, like where the string is bounded. And if we were to zoom in on a little section, let's zoom in on this. We would see, if we could like really zoom in on the atoms or the material, it would almost look like, and this is really an analogy, it wouldn't look like this, but it would behave like a bunch of little particles all connected by little springs. And let's say we couldn't zoom in on this. We could imagine this. We can imagine kind of like a spring. You pull it back, and then it moves back. We pull it back and you release it. It moves back and forth. You can imagine if you have multiple springs all connected. If let's say we pull down on this one, these neighboring ones would kind of follow. They would want to go down too. So if we pull down on this one, I'll draw that. We pull down on this middle one, then these ones would want to follow too. They would want to follow its pull. And likewise, then the ones farther out would also want to follow, and they would all follow, and eventually all the following, the springs following each other would get to the end. And once you get here, this thing's not going to move. It's a fixed point. So at this point, the only option for the spring is to compress in and move the other way. So then its neighbor is going to say, oh, this one moved up, I got to move up. So it's going to move up, 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 and it's going to go all the way across. And if you look at this and kind of think about what we said before, that's what we saw here. We pull our string up into some position, we let it go, and it all kind of comes down, and then it all goes up, and then down, up and down, up and down. So this little model seems to just intuitively kind of make sense. A bunch of springs and little dots, which are masses, a bunch of springs connecting all the masses, all kind of connected in this big structure to make up our string. Well, lucky for us, springs are pretty easy to model. If you remember from high school or college physics, the force on a spring is just equal to the negative of some spring constant x times the displacement. So all this means is if we have a spring, we displace it out, let's say this is equilibrium position, however far we've moved it out is how strongly, because of the negative sign, it's going to pull back in the opposite direction. So if we pull it out this way, the spring is going to pull back this way. We release it, it's going to come back, and then at this point, well, now we've compressed the spring. So now we've kind of, the minus, we've compressed it, so it's like the displacement is in the negative direction. And then we have a negative here, so negative is a positive, so it's going to push itself back out. And that's where we get the oscillatory motion of a spring. We pull it back, release it, and then if we plotted the displacement of this spring over time, so y the displacement, t time, we would see initially we've pulled it back here. That would be the displacement, and then it's going to come back, and then go the other way, come back, and the other way, come back, and the other way. And that's, oh, what do you know, it's one of these, it's also one of these sine waves. So that's also kind of a good sign. The model that, when we measure the sound of the string with our microphone and then plot its frequencies, also is a bunch of sine waves, also is a bunch of sine waves. And then the single spring is a sine wave. So we can always imagine if we somehow fix our springs to be have the right frequency, the right spring constant so that they oscillate back and forth at the right frequency, then our string is just really a bunch of springs which are the right frequencies all kind of bouncing back and forth, making these nice sine waves. So that's kind of the overview. So going back to this model here, we said we have a few springs all connected back and forth. So we can say, if we look at just one spring in the middle, connected to two neighbors, these little zigzags are like the springs, and these little dots are the masses. So we can say this spring, this mass, this nth mass, we call it x sub n. The mass to the right is x n plus 1. And then the mass to the left is x n minus 1. And so if we wanted the force on this xnth mass, it would just matter how far it is from its neighbors and their spring constants. And for simplicity, let's just give them the spring constants of all these little springs, the same thing, just k. So we can write down the force on the nth spring is equal to how far it is from its neighbors. So minus k, because we have this minus k here, so we know we're going to need that. And then if our xn spring is really close to xn plus 1, it's going to want to get pushed back. So so we can write down when this distance is small, we go left. So we can say if xn plus 1 minus xn, if that distance is small, then we go this way. And then we can say likewise for this one, if this distance is small between xn and xn minus 1, and this is compressed, it's going to move to the right. So it's the k gets it, instead of being a minus k, it's a plus k. So xn plus 1, xn, that's our spring, minus xn minus 1. And now we can rearrange this. So we can say, or collect terms really. So we have xn, which has a plus k coefficient, and xn with another plus k, so two of those. So we can say plus 2k xn, and then a minus k xn plus 1, and a minus k xn minus 1. So we can write that minus k xn minus 1 minus k xn plus 1. And then also the force, if you've seen a little calculus, let's write it this way. The force of the nth spring is equal to the mass of the nth spring, but if we give, or the mass of the nth mass, but if all the masses are the same, it's just the mass, times the acceleration of the nth spring. But this is what I was about to say before, if you've seen some calculus, you know that the acceleration is just the second time derivative of the position. So we can say x double dot. These double dots are just the second time derivative, so you might have seen it as d squared x dt squared, or we can say it as dtt x. So these are all the same. And this isn't man, this is m a sub n. So plugging, let's put this x in for the a. We get x double dot, so the acceleration of the nth spring, times the mass is equal to minus, actually let's put the k out front, k minus xn minus 1 plus 2xn minus xn plus 1. Great. And then let's just move the m over, so we have k over m. Great, so we got this little equation. And what we can do now is say, what if we make the distance between these springs really small, really small? Okay, sure, why not? Because we can imagine again with our material that the string is made out of. In reality, these springs and masses are really close together. So we can say xn minus xn minus 1, so the distance between them goes to delta x, delta xn. And if you've seen calculus, this might almost look kind of familiar, because if we say now it's a calculus lesson. If I say that what's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, you might proudly proclaim this is just df dx, the derivative of f with respect to x. So we're about to use this. We almost have that. And if I had the second derivative, it would actually look like, so if we wanted the second derivative, d squared f dx squared, that's going to look something like the limit as, again, delta x goes to 0 of f of x minus delta x minus, and I might have the minus or plus sign here backwards, but it's okay. We'll recover it if it's backwards. Don't worry about it. Minus 2 f of x plus f of x plus delta x all over delta x squared. Wow, this is looking kind of familiar. I mean, if if we look up over here, and then we say xn is really just x, or we can call it y of x. That's a little confusing notation. Essentially, I'm saying the displacement, and I probably should use y's for all this instead of x's, because x we usually think of the movement along the horizontal axis. So maybe I'll just rewrite this here so it's a little less confusing. Sorry about that. So we have y, the displacement of our spring, sub n, is equal to, and then we can just copy this, k over m, and then minus yn minus 1 plus 2yn minus yn plus 1. And then if we look at this equation here, it looks kind of similar. I mean, if we say y of n is really y of x, so it's some x, the x position, then y of n plus 1 is going to be y of x plus delta x. And likewise, y at the, if we go one left position, yn minus 1, is yx minus delta x. If we make these n's kind of as small as we can go in this continuous limit, then this equation we've written here looks almost like our second derivative. We have y double dot, the second derivative of y with respect to time, is equal to k over m, and then we have minus y n minus delta x, or sorry, not n, yx minus delta x, plus 2y of x minus y of x plus delta x. Oh, this looks just like our second derivative. What's going on here? This is looking pretty good. And I think I actually, because I know the result is supposed to look like this. Second derivative of y with respect to x is equal to second derivative of time with acting on y, or second derivative of y with respect to time. I had a minus sign backwards here, so that's okay. If I was really precise with the math, I wouldn't have made that mistake, but you know what, we can make these mistakes, and I could go through the Newton's laws again, and it'll be okay. So we can say, finally, y double dot n equal k over m, and then if we multiply top and bottom by delta x squared, that's just multiplying by 1, then we get, I'll just grab this, because you know we're on a computer with digital math, we can just copy things. It's kind of nice. Whoops. Come on, computer, you can do it. Maybe it'll let me grab it this time. Nope. All right. You know what? I'm not so good at this program clearly, so I'm just gonna rewrite it. So much for digital computation. Yx minus delta x minus 2y of x plus yx plus delta x. And oh no, what do you know? We got the second derivative here. So this little factor, this little factor is exactly this factor. I'm going to try to copy and paste this. No, not that button. I'm going to try to copy and paste this again. We'll see if it works. Select. No, that's not right. Man, Microsoft, why am I not so good at your products? That's okay. This little factor and this little factor are exactly the same, so we can just replace them. We can just replace them because they're the same. Y double dot n, and remember we went from n to x, so this surely be x, is equal to k over m times delta x squared times d squared y of x dx squared, because we had this is equal to d squared f dx squared. So we got this. Now we have this one more delta x term. So what are we going to do with that? Well, this actually kind of cancels out with these k and m's, because we can imagine our spring constant k. The units of that are really force per unit length, because remember we have force equals minus k times x. X has units of length, L. Force has units of, let's just call it newtons or force. So naturally, I mean, if you divide n by L, then K, for these two sides to be equivalent, K has to have the units of newtons or force per length, for newtons per length times length to cancel, and we get two expressions that have the same units. So again, this K has units of force per unit length. And so when the length between two springs gets really small, that K also gets really small. So we can say K goes to like delta K over delta X. And then, or we can just call it K over delta X. Some K, where's my eraser? Some K, that was not the eraser. Why is the eraser not happy? Eraser. K, when X goes really small, gets divided by delta X because we have the units of L. So that would mean K over M times delta X squared goes to K over M delta X times delta X squared. So one of those delta X's cancels. We have some like intrinsic property K over M delta X. Okay, now we need one more delta X to cancel. Well, we can do the same trick here. We have the mass of our particle. It's getting really small. The mass is really a mass scaled by delta X, because we can imagine as delta X goes to 0, the only way for the mass to have any amount of value, the mass has to kind of blow up. So you have this expression. And then what do you know? If we plug this in to up here, we have K over M, that's like a more intrinsic M, over delta X. And, oh, whoops, I put this delta X in the denominator. That's not right. This should be delta X. And then I have this one. Sorry, that's a little backwards. This is backwards. Maybe I'll do a little cut here. So we have this. We have K over M times delta X. And we can imagine as our, going back to this little springs with our masses, as the distance gets really small, the total mass should stay the same. So like of all these masses, so essentially the whole length of the string should have the same mass, but each little mass should get really tiny. So mass really goes to some total mass times delta X. And then K over total mass times delta X. And then we have another delta X here. Those cancel and boom, what do you know? We got Y dot dot equals K over M. That K is terrible. K over M times D squared Y dx squared. And if we write this with a little fancier math, we would say this is dtt, second derivative of y with respect to time, is equal to K over M times d, the second derivative of y with respect to position. And if we look back up here, somewhere up here, all the way up here, that's exactly this equation here. We have dx, I'll copy that so it's a little more convenient. We copy this. Okay, so here's the trick, Microsoft. We have to scroll down here, click text mode, click here, then hit paste, and then it's good. Okay, so we have this equation. So again, looking at units or just matching up the equations, K over M has to be like this velocity term. So we've basically done it. And if that didn't make a whole ton of sense, that's okay. I went through that pretty quickly. The main thing I wanted you to get out of that is this intuition that we can model our string as a bunch of little springs. And when we pull one back, it pulls on its neighbors and then causes this oscillatory motion. And And if we model our string like this, we arrive at this equation. And what we wanted to see again was that if we plot the strength of a frequency against frequency, these equally spaced f0, f1, f2, on and on, of the frequencies that this string oscillates at. And so we can actually do that really quick. We can plug in a solution to this. If you've seen this before, you'll know this. If you haven't, it's going to be like, whoa, that's crazy. That was my reaction. So if we plug in y of position x and time t is some sine wave, let's say. Let's call it some coefficient in front, a0, sine. We can call it k, which is different than this k, but that's okay. I'm not sure what other letter to use. That's the typical letter. Minus omega t. If we plug in this potential solution into here, well, let's see what happens. If we take the second derivative of a sine, we get back another sine. Well, I'll just do it. Ready? dxx of a naught sine kx minus omega t. Well, when we take one derivative, we get a cosine, and it pulls out a factor of k. So we get dx a naught times k times cosine kx minus omega t. And then we do the derivative again, we get a naught, cosine becomes sine, we get another factor of k, and a minus sign because the cosine becomes sine, we get a minus sign. This is just calculus. If you haven't seen it, that's okay too. Just remember the spring analogy. Minus k squared times sine kx minus omega t. And then we can do the same thing. Apply this time derivative onto this. So we get 1 over v squared dtt of a naught sine kx minus omega t. And it's the same philosophy. We're doing a derivative with respect to t. So instead of pulling out the k's, we pull out the w's. And so we get a minus w and another minus w, so that's w squared. And then we get another minus sign from when the sine becomes cosine, and then back to sine. So we get 1 over v squared a naught minus omega times minus omega squared sine kx minus omega t. And then we can just match these two up because we said over here that these two have to be equivalent. So clearly we have sine matching with sine. Okay, those are equivalent. Okay, that's good. A naught matches with a naught. And maybe it just helps if I write this down. It's a naught minus a naught times k squared times the sine of all that stuff is equal to minus a naught omega squared times sine of all that stuff. So the sines cancel. Do that in a different color. Sine, sine. A naught cancels. A naught, a naught. And I forgot to put the 1 over v squared on the right hand side. Remember, there's a 1 over v squared on the right hand side times 1 over v squared. So these equations are true so long as k squared is equal to omega squared over v squared, and then these minus signs cancel. So okay, that seems okay. Great. So long as this k parameter and this omega parameter and v squared all kind of match up nicely, we're good to go. So what is k? Well, I don't know, but we can do one thing. If actually, let's back up. Okay, let's back up. So I made a little mistake, so I had to do a little erasing here, so that's okay. These things happen. Just a little easier if I rewrite some of this. So we arrived at this equation from our little spring analogy, and we want to see what happens if we plug in a solution. And this solution happens to work. So y of x of t, so the displacement of the strings at position x at time t, is equal to some constant out front times sine kx. This k is different than this k, but we like to use k for this, but it's okay. We can think about it as a different constant, and then sine omega t. So let's plug this solution, potential solution, maybe it's wrong, it's right, but this potential solution into our equation. So dxx acting on a naught sine kx sine omega t. Well, you might remember from calculus or otherwise that the second derivative of sine is just another sign, but it pulls out the coefficient inside, and you get a minus sign. So we get a naught, put the minus sign, sine, whoops. We get the minus sign, the coefficient squared, times sine kx. And if you haven't seen calculus, that's okay. Just trust me that this is true. It is true. And remember the spring analogy that got the right oscillatory behavior that we know from our ears and computer recording the sound is correct. And then we have dtt acting on the same expression, sine kx sine omega t. And this is the same thing. So when we take the derivative of a sine 2 times, we get the number in the inside squared on the outside. So, and then a minus sign. So a naught minus a naught omega squared sine kx sine omega t. Great. And now we can equate them from this expression. So the left-hand side not sine, is a naught k squared, and then all the sine terms, equal to the right-hand side, 1 over v squared, which is a velocity, speed, times minus a naught, and then all the sine terms. And then we can see the sines cancel on each side. The a naughts cancel on each side. The minus signs cancel. And what we're left with is, I forgot to put the omega here because I love making mistakes. So what we have is k squared is equal to omega over v. And we put the squares in, but take the square root and you get this. K equals omega over v. So if somehow k is equal to omega over v, then we have a solution. But what is k? Well, there's one more factor that our string we can use. If we look at sine kx and plot it, it would look like something like this, on and on. But our string goes to 0. The displacement of our string is always 0 at its endpoints. So if we plotted the endpoints here, let's say x equals 0, the displacement's got to be 0, it's fixed. And then at the other end, x equals L, it's also fixed. So that means sine kx has to be 0 when x equals 0 or L. Well, let's plug this in and see what happens. Sine k times x is 0 is sine of 0, which is obviously, I don't know if it's obvious. To me it's obvious. It's 0. If you haven't seen trig in some time, it's not so obvious. And then we have sine k when x equals L is also equal to 0. That's a little less trivial, less obvious. But you might know that when the argument of this sine is equal to an integer multiple of pi, we can call that n pi, then sine of n pi is always 0. So k L equals n pi, because sine of n pi is always 0. So k, a little straggler v here, get rid of that. K equals n pi over the length of our string. Boom. And now, we can further plug this into our solution, k equals omega over v. So n pi over L equals omega over v. And recall v, what we call our speed or velocity, is just some intrinsic parameter of our string, these spring constants and the masses that we kind of took to this very infinitesimally, however you say that word, small limit. So omega equals n pi v over L. This is, yeah, you might not see it yet. You might see it, but omega is our frequency, our times-based frequency of our sine wave, and it's an integer multiple of these other parameters of our speed and our length and pi. So I'm going to draw this graph one more time. So in case you haven't seen it, which no shame if you haven't. If this is totally new to you, or even a little new to you, it might not be obvious. It's not obvious. It's really cool. That's why it's cool, because it's not obvious. We had F0 had some. This is frequency, and this is the strength S of our frequency. We had a peak at F0. We had a peak at 2 times F0. A peak at 3 times F0. And if we set pi v over L to some number, call it F0, why not? Then we have omega is equal to n F naught, or n, which I wrote as m before, or no, I wrote it as n. N is some integer. So our frequencies of our sine wave are always an integer multiple of F naught. So with this model, we wrote down a solution, a valid solution is our sine waves that have a frequency. Remember, the frequency is I drew it up here. Is this how fast it oscillates up and down in time? Has a frequency equal to these integer multiples. That's the valid solution. That's the solution our ears pick up, our microphone picks up, that nature takes on. So that's the lesson. That's the lesson, that if we have our string fixed and we let it go, it oscillates with frequencies that our ears and computers and everything picks up as these integer discrete frequencies. And we can write down a physical model that captures that. And I think that's really cool. So in some future videos, I would like to delve more into this. Maybe even make some code that illustrates some of these concepts. And what I really want to try is reducing the assumption that the string is perfectly fixed at these endpoints. Or equivalently, we could say that the length of the string isn't constant. Because we said over here, oh, we have a constant length of our string, so we should get these integer multiples of frequencies. But it doesn't make a whole lot of sense, because if we're pulling back our string and it's made of springs, then the length is increasing. So the length really changes. So maybe this can be a little homework problem for you to think about, or even to try with some code, or however you want to look at this. When the length of the string is fixed, we have the solution of this model is a bunch of sine waves. Sine of fn, 2 pi fn, I'll just fn times t. Where fn is equal to, we had it over here, pi, the speed over length. So that's kind of like the first order approximate. That's the first approximation of our model. But what I mean by that is, when we wrote down this model, that this is what we got as a good approximation. But I think it would be kind of cool to kind of combine this first order approximation with the length changing with time. So we can write down maybe something like a bunch of springs connected. More than that, but just some number of springs connected. And then we let our string evolve a little bit in time. And then we can see how long the string really would be. And then put that in as our L. And then let the system evolve a little more, and then put that in, get the new length and that in as L. And I think we might see some interesting properties, because I lied to you before. This whole video I lied to you. I said these frequencies are perfectly integer spaced. And I don't know if I said perfectly because I didn't want to, but I might have said that. But in reality, they're not perfectly spaced, and they can even maybe change a little bit their spacing with time. And I think one way to capture that is recalculating L with time. So that can be a little homework problem. But anyway, I hope this was an interesting video. I hope you learned something. Write a comment if you did, or not, but it would be cool. I've been wanting to make this video for a while, so I hope it was kind of interesting. Have a great day or night. This is 12:01 a.m. for me, so I was excited to make this video. So it's been made. It's done. Enjoy. Good day.